Hello and welcome to T1 Day 12 of Honors Precalculus. We are jumping into polynomial functions today. It's a big day. It's very exciting. A polynomial is the sum of power functions where each exponent is a whole number. This is really important, a whole number. So you could have something that looks like this, 2x squared plus x plus 9. You could have g of x is equal to negative x to the ninth plus 12x plus 7. You could have, I don't know, j of x is equal to x plus x squared plus x cubed. Generally speaking, we like to write them in descending order, the highest powers first and descending, but this is also a polynomial. It's just not written in descending powers. So a polynomial function is in standard form when the terms are written in descending powers. Yay, descending powers. The degree of the polynomial is the largest exponent. So for example, for g of x right here, this is in descending order already. So if we did the same thing right here, negative x ninth plus 12x plus 7, that is in standard form because the powers are descending. That's a power of 1 right there, 9 and then 1. And it is descending because it goes down in that direction. The power, the degree of this polynomial would be 9. The degree of this polynomial here, f, would be 2. And on j of x, if we rewrote that in standard form, same polynomial would be x cubed plus x squared plus x. I'll make that a nicer 2 right there. It's x squared. The power here, the highest one, is 3. So the degree of that polynomial is 3. Now, the next term is multiplicity, and it is the multiplicity of a factor of a polynomial. We've seen how some polynomials, you've seen this, let's say, I don't know, maybe, I don't know, q of x? Let's do m of x. I like that. Just picking different letters here. You can have polynomials, for example, that look like this, x squared plus 5x plus 6, and they factor into something like this, x plus 2 times x plus 3. When they're factored, you end up with terms that look like this, x minus a to a power. So for example, here we have x minus a. In this case, we have x minus negative 2 to the first power. So sometimes you have polynomials that have an x term, just an x term. So if a polynomial has a 0 with an even multiplicity, for example, the 0 right here is negative 2 because it makes it 0. You could have a 0 with an even multiplicity. You could have, for example, n of x. You could have x minus 2 squared, for example, times x plus 3. This would be a polynomial. You could multiply this out to see what all the terms equal, but if x minus a is a factor of a polynomial, then a is called a 0, because in this case it's minus 2, so this would make it a 0. And in this case it would be x equals negative 3 would make it a 0. If it's an even multiplicity, then the graph will bounce off the x-axis at the 0. And if it's an odd multiplicity, the graph will go through. What does this mean? So if I had n of x right here, what this tells us is, just if I gave you this, immediately it tells you on the graph at x equals 2, and it's going to bounce off, meaning the graph is either going to go like this or it's going to go like this there. It's going to touch it, and you will use other things to figure out which one it is. It does one or the other. And then at x equals negative 3, 1, 2, 3, at x equals negative 3, it's going to go through. So here at negative 3, it's either going to cross like this or it's going to cross like this. It's going to cross. And you don't quite know what the curvature looks like, but odd powers right here, odd powers mean cross, and even powers of these mean bounce is the word we used, bounce off. Now, the way one big way you figure out which one it is it going to be this one or this one, is by looking at end behaviors or plotting one more point. So on these right here, when we state the end behaviors, that's doing the limit as x goes to infinity of f of x. So on this polynomial, you really only look at the highest term power, 2x to the 5th. When x gets really, really big, this is just going to go to infinity when x gets really, really big, because a billion to the 5th is a billion to the 5th. And multiplying it times 2 just makes it bigger. If you go to negative infinity of f of x, what happens when you change this to negative right there, negative x to the 5th? Because it's an odd power, it's going to be like that. So what that tells you is on the graph of this function, whatever it is, you know that as x goes to infinity, it's going to go up, and as x goes to negative infinity, it's going to go down. So what about this one? The limit of g of x, it's the limit as x goes to infinity of g of x. Well, in this case, you're looking at this term right here. What happens as x gets really big? X to the fourth is going to be positive. It's actually always going to be positive, and that negative 3 will make it negative. So it's going to be negative infinity. And then what about the limit as x goes to negative infinity of g of x? Well, when you plug in negative infinity, or look at a number getting really, really big and negative, negative infinity, like negative 10 to the fourth, is still going to be positive. Same thing with negative 100 to the fourth. But that negative 3 is out front still, so this is also going to be negative infinity. So this graph right here, we don't know what the middle part looks like, but we know as x goes to infinity, it's going to go down, and as x goes to negative infinity, it's going to go down. So how do we put this all together? Well, we have this polynomial right here, and it's nicely factored. Look at that. You're not always going to be given it in factored form. The first thing we want to look at as the end behavior. So that's the limit as x goes to infinity of f of x. So as x goes to infinity of f of x, this term is going to get really big and positive, really big and positive. This is going to get really big and positive, but this is going to make it negative as x goes to infinity. So that means in this case, it's going to go to negative infinity. What about the limit as x goes to negative infinity of f of x? I'll use green here. Well, this right here is still going to be positive because you squared it, stays positive, but this is going to be negative, and this is going to be negative. So in this case, this is going to be a negative times a positive times a negative, which is positive. So the end behaviors alone, you're going to end up with, as x goes to infinity, it's going to go down, and as x goes to negative infinity, it's going to go up. So we know it's going to do that in general. We now need to figure out what's in the middle here. Well, we know two of the zeros. Right there, we know it's going to cross at x is equal to negative 3, so right there. And right here, we know x is equal to 2 is another 0 right there. So those are the x-intercepts. And also, what are the multiplicities of each of these? Meaning you have an even power here at negative 3. So here, it's going to touch. It's going to bounce off of it. And here, it's going to cross. The next thing we can do is find the y-intercept. So the y-intercept, which we've talked about before, is when x is equal to 0. So that's going to be f of 0 is equal to negative 0.2 times 0 plus 3 squared plus 0 minus 2. So that's going to be negative 0.2 times 9 times negative 2. So you end up with, when x is 0, this number right there is equal to 3.6. Yeah, 3.6, that's what it is. So that's right about here. So now that you know it has to cross there and it touches here, what does that mean it's going to do? We know that this graph is going to come down, it's going to touch here, it's going to go up, and then it's going to cross, and then it's going to go down. Now, I put these arrows over here, but you didn't know if it was going to be over there. You just know it has to go down. And since we have erasers here, we can make these nice and smooth. So I'm going to make this curve nice and smooth. It's going to go up. So again, touches, crosses. We know the y-intercept has to cross there. So we have a great graph. Now the curvature itself, where things change curvature, more detailed analysis, you need more calculus to do that. Another term, another method we're going to use to analyze graphs is polynomial long division. Polynomial long division. And really the only thing you need to remember for this is it's very similar to regular long division, and you need one phrase: leading over leading. Leading over leading. So you set this up just like regular long division, 3x squared plus 1 dividing into 18x to the fourth minus 21x cubed minus 3x squared minus 7x minus 3. One important note, if any terms were missing, like let's say the x squared was missing, you'd put a 0 in there. You have to put placeholders in. So the leading term underneath here is this term. So that's going to be first 18x to the fourth, and the leading term out here is always going to stay over 3x squared. So again, it's leading, and this the first one is leading over leading. That's our first time. We're going to do this several times. So when you divide this, you end up with 6x squared. And just like with regular long division, you're going to take this number and put it up top and put it above the term that it correlates to, in this case the squareds. And now you multiply. So when you multiply this by both of these, you end up with 18 x to the fourth, which is what we want because we want it to cancel. And then 6x squared times 1 is plus 6x squared. Now you put a line, subtract, and parentheses. These parentheses are super important right here, super important. It'll keep you from doing small algebraic mistakes. Like the one I just did where I just put this underneath the wrong term. I want to put it under the squared term, which is right here, plus 6x squared. So put these parentheses and line it up properly. Now you subtract. These two are going to cancel. Nothing's under here, so it's minus 21x cubed. And then you have minus 3x squared minus 6x squared. So you have minus 9x squared. And then just like with long division, you drop this down. And now you do the same thing again. You do leading over leading again. In this case, the new leading term is negative 21x cubed. So you have negative 21x cubed. This one stays the same. You have 3x squared is equal to negative 7x. Oh, there was a 6x squared right there. I deleted. So then this turns into minus 7x up here. That one went up top right there. And now you do the multiplying again, the same thing. You take this negative 7x squared, negative 7x, and you multiply it. So when you multiply, you end up with negative 21x cubed minus 7x, or sorry, plus 7x, plus 7x. Oh, no, it is minus because it's minus up top. See, it's really easy to mess that up. Now you subtract, and again, use these parentheses. Please put these parentheses in. Now when you subtract, you have negative 21, oh, this is 21, minus negative 21. This cancels. You end up with negative 9x squared, and then you end up with plus 0x. You can drop that, that's fine. And now you can bring down this negative 3. But now you have a new leading term again, which is this. So you end up with negative 9x squared over, same one, 3x squared is going to be minus 3. So that minus 3 goes there, and now you multiply again. So you have negative 9x squared, and then negative 3 times this 1, negative 3 times this 1 is negative 3. You subtract, oh, and look, this cancels and this cancels, 0. When you divide and get 0 as a remainder, that means it divides evenly. So what this now tells you is that it tells you the big polynomial divided by the smaller polynomial is 6x squared minus 7x minus 3. This is polynomial long division. It'll take practice. You do it carefully. Now, when you see something big like this, you might say, is there a faster way? Well, there is if this thing you're dividing it into is a linear term. This is not linear, so you must use polynomial long division. But if the term that you're dividing into the other one is linear, there's a quicker way. This is linear right here. So what you can use is something called synthetic division, which is actually exactly the same as polynomial long division, just faster. So the way you set this up first is you look at this and say, what makes that 0? Negative 4 makes it 0. And you write a bar a little bit differently like this. Next, you look at this polynomial and you say, what are the coefficients in descending order, where they are 10, 29, negative 50, and negative 24. So you just set it up like this. And again, you can only use it when it's linear, when this is linear, a line. The first thing you do is you drop down the first number and you write it there, it's 10. And now you multiply by this number. You multiply by that number, so it's going to be negative 40. And then you add. When you add these two things together, you're going to get negative 11. And now you just do the same thing again. You multiply by this number again, so you get 44. Add these together, you're going to get negative 6. Now you multiply again, and you're going to get 24. Add them together, and you get 0. Oh, it came out to be 0. What's really nice about this is that when you look at these numbers right here underneath, this is the constant, this is the x term, and this is the x squared of what's left. Meaning this translates to 10x squared, not plus, minus 11x minus 6. This tells you what you've done here is this thing you're dividing into, 10x cubed plus 29x squared minus 50x minus 24. We just divided it by x plus 4. And it tells you, based on what's in the green there, that that's equal to 10x squared minus 11x minus 6. Again, this is a faster way of doing polynomial long division, but it's only good if it's a linear term. Okay, one thing I mentioned before is if you skip terms, you have to put in the zeros. So if you set this one up right here, what makes x minus 2 0? What makes it 0? Well, that's 2. You put the bar underneath, and then what are the terms here? What are the coefficients here? You end up with 1 because of the x cubed, but x cubed minus 8 is the same thing as x cubed plus 0x squared plus 0x minus 8. Those are just invisible terms that are there, so you have to put in 2 zeros and then the negative 8. That's really important. Oh, sorry. Sadako had some feelings about this one. So you do the same thing. You bring this down, it's 2. Sorry, you bring it down, it's 1. You then multiply by 2 and you get 2. Add, you get 2. Multiply by 2 and you get 4. Add and you get 4. Multiply and you get 8. Add and you get 0. So again, these terms that are left tell you what the coefficients are. This is the constant, the x, and the x squared. So this now tells you that x cubed minus 8 over x minus 2 is equal to 1x squared plus 2x plus 4. So on number 7, it says find all the x-intercepts given x equals 3 is a 0. When it tells you x equals 3 is a 0, it means that x minus 3 is a factor. And since this is linear, we can divide with synthetic division, meaning we can take x minus 3 and we can divide it into 1, negative 2, negative 7, 8, and 12. Those are the coefficients. And it's, sorry, x equals 3 is a factor. So this, what makes it 0? 3 makes it 0. So when you drop this down, you end up with 1. Multiply by 3 and you get 3. Add and you get 1. Multiply by 3 and you get 3. Add and you get negative 4. Multiply by 3, you get negative 12. Add right here and you get negative 4. Multiply by 3, you get negative 12. Add and you get 0. That's a good sign. So what's left? What is left? Remember, these numbers that are left tell you that it's going to be the constant, the x squared, and the x cubed. So what's left is x cubed plus x squared plus x minus 4 right there. So we now know, if we pause, what do we know in totality? Here's the original polynomial. We know that this is true. So this right here, the original polynomial, is equal to the x minus 3 from the original thing it told you times what's next, x cubed plus x squared plus x minus 4, like this. This is what's left right here. This is what's left. So, oh, and it's, excuse me, it's minus 4. It's minus 4 right there. I did that a little too quickly. It's minus 4 right there. And then this one is minus 4 plus x. So we now have this first thing factored out. So how do you factor cubic? Well, we have factoring by grouping here. So what can you factor out of the first two terms? Well, that's x squared. So that's going to be times x plus 1. We can factor out a negative 4, and it's x plus 1. So what does this factor into? X squared minus 4 times x plus 1. But this right here is the difference of squares. So it's x plus 2 times x minus 2 times x plus 1. This right here is the same as this. So what's the fully factored form? Well, it's going to be x minus 3 times x plus 2 times x minus 2 times x plus 1. So what are all of the zeros there? What make those linear terms 0? We have x equals 3, negative 2, 2, and negative 1. Those would be all the zeros. So how would you use everything we've learned to graph these two functions? Well, the first thing is you look at the limit as x goes to infinity. Remember the end behaviors. What happens to this function here? Well, the only thing that's really going to matter as x gets big is that first term. And as x gets big, the whole thing is going to big. And then similarly, as x goes to negative infinity of this same thing, negative infinity to the fourth is still going to be positive. So this will be also positive infinity. So you know, whatever this does, as x gets big, it's going to go up and up. Now the curve might not make it over there, but you know it's going to go up on both sides. Let's do the intercepts. What about the x-intercepts on this? Well, that's when y is 0. So that's 0 is equal to 2x to the fourth minus 8x squared. It's actually not that bad. You can factor this. So what do you factor out? I'm going to factor out a 2x squared, and you end up with x squared minus 4. So that's 2x squared times x minus 2 times x plus 2. So what are the three zeros here? X equals 0 because of the first one, and then 2, and then negative 2. So where does it cross? It crosses at negative 2, 0, and 2. And what is the multiplicity here? Well, the multiplicities are even right at 0. That's even right there. This one is an even number, so we know here it's going to touch. But at the other ones, these are powers of 1. For these, they're going to cross. Are there any other x-intercepts? There aren't. So you know that since this function up here is going up here and it's going up here, you know it's therefore going to have to come down and cross here. You also know it's going to go down and cross here. So what other thing we could do? Well, we could try to find other even. We find if it's even or odd. Is this an even function or odd function? Meaning, is there any sort of symmetry? It's a callback to what we did before. You plug in negative x into the function. You get 2 times negative x to the 4th minus 8 negative x to the 4th squared. And that's just going to be 2x to the 4th minus 8x squared, because when you square or raise it to the 4th power, it's going to be the same because it's an even power. So this tells us that f of negative x is equal to f of x, which means it's even, meaning it's symmetric over the y-axis. So what is this going to look like? Well, what's the only thing it can do? It can't cross the y-axis anywhere else. It has to touch up there. So this thing is going to go down, and then it's going to go back up. It's going to go down, it's going to go back up. So it has to touch, cross, and cross. Now, do you know how far down it goes? Not really. You could plot some points. Does it turn like this? Probably not. So it's going to go up, and it's going to be the same on both sides. It's going to go up. So I'll draw that a little higher. It's going to be, the symmetry is not the best in my drawing. If you want more practice, you can do the same thing here, where you do the limits. You do the limits as x goes to infinity for end behavior. Does it touch or cross? You have to factor this. This is good for practice right here. If you want more practice, do this one.